a quadratic map. Okay? And then this poses a very interesting idea. Then you compose two invertible linear maps, L1 and L2, to hide this map. Okay? What L2 does is essentially change your basis. And what L1 does is mix the polynomial together. Okay? And this is it. This is the cipher. The F bar is the cipher. Okay? And now they impose the following condition, which is what? Q to the theta plus 1 is co-prime with respect to Q to the n minus 1. Because the finite field size is Q to the n, and the element of the non-zero element form a cyclic group. If we know if you raise the power, and if the power is co-prime with the size of the group, it is an invertible map. So that map is invertible. Okay? That allows us to what? Find the ciphertext, find the plaintext with a given ciphertext. And here, the inverse is easy to do. It's the same as ISA. Okay? So this is their idea. Okay? So the public key including all those components of this map, which is a Kn to Kn, and it is quadratic. And the secret key is just these two maps, linear maps, L1, L2. That's it. Everything else is public. Okay? So remember, L1 does is to mix things together, L2 is the change of basis. Okay? And if you notice from the earlier definition, L2 is invertible, phi is invertible, F is invertible, every map is invertible. In this case, if you want to decrypt message, you just invert what? Invert the map one by one. And very easy to do, because L2 is linear, so you can invert it easily. And F can be easily inverted because you just raise x to the t. And L1 also can be easy. So decryption process is basically invert the map 3 times. Okay? So this is it. Okay? And the toy example earlier I showed is the case you set n equal to 3 and theta equal to 2. That's the example I showed you. Okay? And the interesting about this is that once they invented the system, everybody was very excited because efficiency. It was, you can show easily. They were suggesting that n actually, the block length is actually 64 is enough. They were very excited because they were far faster than ISA. Okay? And they actually immediately submitted this one as one of the candidates for Japanese security standard. Okay, they were discussing it for several years. In 1995, right before the Japanese decide, I think the Japanese government more or less decided to accept it as a security standard. Right before that, there's a French mathematician called Perturbation. He found a way to broke the system. And what he found out is that if you have plaintext and ciphertext, here's xi's are components of plaintext, and yi's are the components of the ciphertext. And these satisfy a very special equation called a linearization equation. Okay? And we can find out easily those linearization equations by just using samples. Okay? Just plug in pairs of plaintext and ciphertext. And you can find those equations easily. And look at this equation. Suppose so this yi's are ciphertext. If you find those equations, if you have the ciphertext, if you plug in the ciphertext, what you will get is what? A set of linear equations satisfied by what? By the plaintext. That's it. You can break the system because you can have a substantial number of linear equations, linearly independent linear equations satisfied by plaintext if you are given ciphertext. So you just break it. Okay? And it's very easy to do. Okay? This happened in 1995. Okay? Okay? However, Matsumoto Ibai system, I think, is the catalyst for the development of the field of multivariable crypto system. So Pataran, as the person who broke it, and immediately he and his research group developed many, many new systems which are very much inspired by Matsumoto Ibai system. Okay? And so here I want to introduce the first generation. The first generation called minus plus. Okay? So, and what does it mean by minus? Minus, which means you have a bunch of equations, you take a few of them out. Okay? You take a few components out. This is minus. And what is plus? Plus, you just add random equations to it. Very simple idea. Okay? The minus idea actually was first proposed by I.D. Shamir. Okay? It didn't work, but the idea itself originated from him. And what is S-flash? S-flash is just Matsumoto Ibai minus. And what they did is just you have a map, and you take a few components out. And then the linearization equation cannot be satisfied anymore. However, we can see easily if you take a few components out, the map is not going to be bijective anymore. Okay? But you use it for signature. It's used for authentication. You do not use it for what? You do not use it for encryption. Okay, so this is what they use. Okay, this is last year. Yeah, in 2004, they were accepted as security standard for low-cost smart cards by the Information Security Technology Program of the European Commission for the new European schemes for signature, integrity, and encryption project called the NESI. Okay, this is last year. Okay, and the length of the signature is 249 bits. Okay, and so here, because it's a signature scheme, and to verify a signature, what you essentially have to do is you have a pair of vectors. You just put them into the equation to make sure the equations are equal, if the equation is valid. If the equation is valid, then what? The signature is valid. Otherwise, you deny it. Very simple. Okay? And here, how do you sign it? To sign it is very simple, because if you keep the secret key, you know which component you take out, which means you know what is the minus you have done. What you do in order to sign a document, what you do is what? You put them back. Okay? And you randomly choose a set of values, and you can sign it easily. Okay? So this is a S-flash. Okay? So there's another generation for encryption purpose, and this system is called HFE. HFE stands for hidden field equation. So if you look at the multimodal EMI system, the critical map is the map F, which I explained earlier. The map X, map to X to the Q to the theta plus 1. Here, Perturbation said, instead of using F like that, he proposed a new F, which looks like this, which is summation of X to the Q to the I plus Q to the J, and plus sigma summation of X Q to the I terms like that. Here, the summation index has to be small, because in this case, when you invert the map, you need to solve a polynomial equation, which can be done fast if the degree is low. Therefore, this parameter D must be relatively low. But unfortunately, Kipnis and Shamir attacked the system. They showed that if the D is too small, it's not good. Okay, so D has to satisfy some minimum requirement. Okay, and what eventually they produce is a new system, but it is secure, we believe. Actually, we believe at this stage this is one of the strongest systems, but it's very fast. Okay, however, what they did later is also very interesting. They developed something called HFE-, which means based on FHFE, you take a few components out, you build a new signature scheme. And this signature scheme is very short. It's only have about, the system listing is about 80 bits. The signature length is only 80 bits. Okay, very short. But the signing process is relatively slow. Okay, so this is the case. And later they have further generations. And here I want to mention XL. XL stands for extended linearization attack. Okay, this is very much related with global basis attack. Okay, and there's also something new called oil vinegar, and which is for a signature scheme. And then there's another new scheme called HFEV, which is a combination of HFE and the oil vinegar. So this is just examples of new scheme, which I don't want get into the details. Okay. Now I would like to start the second part. It's internal perturbation. Internal perturbation is a new idea we developed recently, and the purpose of this is to increase the security of the system and therefore increase the efficiency of the system. Okay. Okay, what is the general idea? So perturbation originally is an idea from physics. What do you mean by perturbation? So you have a continuous physical system, and often you do something called perturbation. What you do is you add a small noise. You change the system a little bit by a very small scale, such that you observe how the system reacts. So you use that trick to study the system. Okay, and what we suggest to do is to transplant this idea from a continuous system to what? To this discrete system. Okay, and this idea was first proposed in POP PKC 2004. And here, let me fix one thing, which is I would like to fix Q equal to 2 at the very beginning. That means the size of the small field is of 2. Okay, so in a continuous system, you can have something called a scale. In a discrete system, there's no scale. So how do you do the things like that? Okay, our idea is very simple. We choose a small integer r. Okay, this R, and then we find a subspace, a linear subspace of linear functions. Okay, so this is Z1 to ZR, ZR linear functions.